In this subsection, we will talk about linked stacks and queues, which means we will implement stacks and queues with a linked list. In the previous lectures about stacks and queues, we used array. So we could allocate memory space statically or dynamically, but it was an array, right? But in this section, we'll use a linked list. As I said, we could implement stacks and queues with an array, which is a sequential stack or sequential queue. Okay, and then the problem of that kind of stacks and queues is that the maximum size of this stack is fixed. Even when we allocate memory space dynamically, then we have to give the number, the maximum size of the stack. Okay, and then once we allocate memory space, then the size is fixed. So then when the stack is full, then there is no other way. We have to reallocate memory space for the whole stack. Okay, that is the main problem. And the second one is quite similar to the first one. If the multiple stacks and queues coexist, then memory is utilized inefficiently. So basically, the first one and second one say the same things. Basically, if it is based on an array, okay, if it is a sequential stack or queues, the memory is utilized inefficiently, and it is fixed. Okay, it's not flexible. So as an alternative, we have a linked stacks and queues. So basically, we will use a linked list. So in this slide, we have a linked stacks and queues as graphs. Okay, first one, let's take a look at this linked stack first. So we have a top, which is pointing the first node, and the first node is pointing the second node. Is exactly the same as just the linked list as we've seen in the previous sections. And instead of a head, we have a top. Okay, so top is pointing the first node. Okay, so it's basically head. And the reason why we use top is that the stack needs top. So when we add a new element, if we push new element into this stack, then we will add that element at the beginning of this linked list. So we insert that node right before the first node. So between top, actually not between, right before the first node. Top will point to the new node, and the new node will point to the first node. Okay, that's it. That's simple linked list based stack. And what about queues? In the queue, we need 2 pointers. Do you remember in the stack we have one open side and one closed side, and in the closed side there is no operation, so we don't need any pointer. But in the queue we have 2 open sides, and first one for insert and the other one for delete operations. So we have a front and rear, and front is head and rear is pointing the last node. Okay, and when we insert in the queue, we add a new element at the end of this linked list. Okay, since the rear is pointing the last node, and the new node will be added, and it means the last node link will point to the new node and rear will point to that node. That's kind of the algorithm. And when we delete, then we delete the first node of this linked list, and then front will point to the second node. Okay, that's the algorithm of queue based on the linked list. Okay, let's implement a push operation with a linked list. So in these functions, we pass one element, E, and E is the element of this stack. And we allocate memory space for a new node. Okay, and then if the new node is null, it means we are out of memory space, so we cannot push anymore. Okay, and then once we have a memory space for a new node, then we assign the data. Okay, so E will be copied to the new node data. Okay, and then next one, new node link will point the first node. Okay, top has the address of the first node, so new node link will get that, which means new node link will point the first node. Okay, and then that's not it. The top should point to the new node. So if you follow these red arrows from top, we have a linked list. Okay, so that's how we push. Then what about the pop operations? We don't have a parameter here, and we declare one element E. Okay, and then we have one pointer del. Okay, and then first we check if top is null. It means actually we are checking if it is empty. Okay, if it is empty, then we return just nothing, and otherwise we copy top data to E. Okay, top data is the type of top data is element, so we just copy that, and then del is a pointer, so del will point what top is pointing, which means del is pointing the first node, and then next one, top link is pointing like this. Okay, so now we have a new stack. So we just deleted that. We just deleted the first node from the stack. Okay, so top is pointing the next node, and that's not it. Since we are allocating memory space when we insert, we have to deallocate the memory space when we delete, when we pop, right? So we have to deallocate memory space, which is pointed by del. And then we have to return E. In the previous slide, we talked about two operations of stacks, right? So push and pops. And now let's talk about queues. So we'll talk about two major operations, add operation and delete operations. Okay, first one is add operations. We have to pass the data part as structure instance E, and since we are adding new element, then we have to allocate memory space. Okay, so we allocate memory space for a new node like this, and then we check if this memory allocation is successful. If not, then we have to return. Okay, now let's assume that memory allocation is successful, and then we have to assign the data. So first, new node data will be E. So we copy all the elements of this structure instance E to new node data. And then, when we add a new node to this linked queue, new node will be the last node. Okay, so the rear is pointing the last node, and the new node will be after this last node from the linked list. So the new node link should be null. Okay. Then next we check if front is null or not. If front is not null, then we have something there in the queue. And then if we have something there, then when we add a new node, then the pointer front has nothing to do with these insertions. Front is all about the delete. Okay, so if front is pointing something, then rear link will point new node like this. Okay, and then the next one is, this is not it. So in this figure, rear is pointing the one before the last node, so we have to change this one. So now rear is pointing new node. Okay, so this is it, and we just added a new node at the end of this list, and then rear is still pointing the last node. After adding the new node, then still rear is pointing the last node of this linked list. Is perfect. But what about the front is null, which means we don't have anything there? Then when we add a new node, then the front should point to that node, right? So there was nothing. So front was pointing nothing. So front was null. And then when we add a new node, then front should point to that node because since we have only one node. Now front is pointing new node and the rear is pointing new node. Okay, that's it. Next one is delete function. Delete function is quite similar to the pop from the stack. Okay, so we have element E and we have a pointer del, and then we check if a front is null. If front is null, it means we have nothing there, so we cannot delete anything. Okay, and now let's assume that we have something there. So front is pointing something. Front is pointing the first node of the linked list, and then we will delete the first node. Okay, and the front data will be copied to E, the structure instance E, and then del is pointing the first node. Okay, so E is copied and the del is pointing the first node, and then front will point the second node. So now we just updated our queue, but that's not it. Okay, front is pointing the next node, the second node, but we have to delete. Okay, we have to delete the first node. We have to deallocate memory space, which was allocated for the first node. Okay, that's it. And then we return. But in the middle of these lines, we check if front is null. Okay, since we have two pointers in the queue, then we need to check if a front is null. If front is null, then now we delete the only node. Okay, before this delete operation, we had only one node, and then now we want to delete the only node. So then the front is null, then the rear should be null too. Okay, otherwise rear is pointing something, then there is a dangling pointer problems. Okay. In this subsection, we'll talk about circular linked list. Okay, so we talked about quite a similar thing before. So in the queue, in a array-based queue, if the queue was not circular, then there was a problem. I mean, whenever we add or delete, then we had to shift the elements, so which leads to a huge amount of memory access, and it takes a lot of time, right? So to avoid that kind of unnecessary memory access, then we used a circular queue. Okay, so we actually changed the index with modulo operations. But now we'll talk about circularly linked list. So this linked list is sequential, right? So if we follow these pointers, the links, then this is just one directional. So we have the first node and the last node. And in the circular linked list, it is a circular. There is no first one and the last one. Okay, then what is a circular linked list? What does it look like? Okay, the circular linked list is a linked list in which the last node points the first node. Okay, so that we can traverse the whole list starting from any node. So basically, there's no head node, there's no first node, and there's no last node. It's just a whole circular. Okay, so it looks like this. So in this graph, it looks like the bed is the first node and the vet is the last node. But there's no difference between the bed and vet because this is not an array. So in the memory space, we don't know which one is where. Okay, so it's just a logical. So as long as it is a logical connection, then nobody can say which one is the first node. Okay, and we can just we can have a pointer last to point one node. Okay, then the last is pointing the last node. But in the memory space, actually, there is no difference. But logically, okay, so we have one pointer last, and it is pointing the last node. Okay, so usually a circular linked list is handled by pointer to last element. Okay, And then if you want to have a head pointer, then head can be obtained from last link. Okay, so it's just logical. Okay, let's assume that we have a circular linked list, and now we want to traverse. Think about something like a print operations. Okay, so we have a list node pointer car, and the car starts from last link. It's supposed to be a head. Okay, and it starts from the bed in this graph. At the bottom of this slide, we have a bed, which is the kind of the first node. Okay, and then we print out the bed, and we move to the next node by assigning a car link to car. Okay, and then so we iterate this loop as long as car is not null. Then what happens? So we print out bed, and next we print out the cat, and then the set and the vet, and then we go back to bet. Okay, because there's no checking point. Okay, so this is a problem because we will have an infinite loop here. So when we traverse, then we have to check. Okay, we have to check some point. Okay, so let's try in a different way. So car start from last link as before, and then instead of checking if car is null, then we check if car is last. Okay, then what's the problem here? Is it correct? Actually, we cannot print out the vet. Okay, let's follow these iterations. We start from a bat. Okay, so we print out bat. Okay, then we check it's not the last. Okay, then we move to the next one. Now we print out the cat, and the car is not last. So we move to the next one, and we print out the set, and then car is not the last. And then we move to the next one. Okay, so now car is pointing the vet, but car is the last. Okay, so we quit without printing vet. Okay, so this is kind of problem. Okay, so we need an additional handling to avoid this kind of problem. Now we will use a sentinel node or dummy node or just empty node. Okay, so do you remember when we had a circular queue in chapter 3? So we had just one empty node. Okay, if the queue is full, then still we had one empty node. Okay, so we keep one node empty to distinguish two different conditions, full and empty. Okay, so if we have only one empty node, then it is full. Likewise, we will keep one empty node here. Okay, so let's follow. The sentinel node is a node at first or last, which is not used to store data, but to simplify or speed up some operations. Okay, so in this graph at the bottom of the slide, we have a sentinel node. Okay, so the empty node is the head node. So head node is pointing the first node, which is a bat, and the last is pointing a vet. Okay, so the last node is pointing the sentinel node instead of bat. Okay, so let's implement these traversal operations with this sentinel node. Okay, we have a list node pointer car, and it starts from head link. Okay, head link means the bat node. Okay, so we print out bat, and we check if car is not head. Okay, then we move, and then we print out the cat, and we move a set, we move a vet, and then when we move to the next one, then the car is head, right? Car is pointing what head is pointing. So basically car is the same as head. So we stop. So we print out bad, cat, sad, that, stop. Okay, we quit. In this slide, we have a really interesting idea about circular queue. Okay, so think about this queue or stack, and when we insert a new node, the first thing to do is to allocate memory space for the new node. Okay, and then when we delete or when we pop, then we have to deallocate that memory space, which means every time. So every time, for every operation, we have memory access. Again, as I said before, the memory access is really time consuming compared to other operations. I know you cannot feel the time in your homework assignment. It's really fast, but compared to other operations, it takes a lot of time. It's really slow. So we want to avoid unnecessary memory access. Okay, that's our goal here. And instead of deallocating and allocating memory space again and again every time, then we will actually keep that memory space. Once we allocate memory space, then we will not deallocate the memory space until we are done with this program or software. Okay, so here's the deal. We can keep another linked list R as a memory buffer. So in this slide, the second second circular list is the R, memory buffer. And when we need a new node, our main circular link is the first one. Okay, the upper one is our linked list. And when we need a new one, then we will get one from R. Okay, so R is memory buffer. So we will get one node from the R. So then actually we have to change. We don't need to allocate memory space. Instead, we just change the link. Okay. Then let's say we insert a new node to our linked list. Then we just get one from list R. So now R will have just 2 nodes, and our linked list will have 5 nodes. Okay. And in this operation, we don't have memory allocation or memory deallocation, just to change the links. Now the memory buffer is in the memory space, and our linked list is in the memory space, in the same kind of memory space. So they can point the other, any of these nodes. Okay, it doesn't matter where it is. It is in the linked list or it is in the memory buffer. So it doesn't matter. So we can point that. So if you want to add one new node between bed and cat, then we can get one from the R, from the memory buffer. Let's assume that we will get the first one, then the bed will point to that first one, and the first one from the memory buffer. So first one will point to cat. Okay, then we just inserted new node between the bed and cat. But at the same time, the head of this memory buffer should point to the second node, so that we actually added a new node to our list, and we deleted one node from the memory buffer without any memory access. Okay, that's perfect. Okay, when we delete one node from our linked list, instead of deallocating that memory space, we just change the pointer. So let's assume that in this graph, we want to delete the cat. What should we do? Then let's assume that we will add that node. Whenever we add a new node to the this list, then we will add that at the beginning of this list. So it means when we delete the cat, bed will point to set. Okay, so cat is removed from our linked list, but at the same time, the head of the memory buffer will point to cat, and then the link of cat will point to the first node of the memory buffer. Okay, so we just moved this cat node from our list to the memory buffer. Okay, so we didn't allocate memory space, we didn't deallocate memory space. We just moved diskette from our list to the memory buffer. Okay, so perfect. So only when R is empty and we want to add a new node to our linked list, then we will call malloc or new to create a new node. Otherwise, we don't have to allocate memory space at all. Okay, so we will keep the two linked lists. And the first one is our main linked list, and second one is just the memory buffer. So it's kind of memory waste in a sense, but it will improve the computational time a lot, right? That's the beauty of this memory buffer. Okay,